So hello everyone, we're group 2, the noisy networks for exploration. So today we're going to present Noisy Networks for Exploration, a research paper from DeepMind that uncovers a new approach for reinforcement learning agents to explore their environments more intelligently. We'll walk through the motivation behind this work, the core idea of noisy network, its implementation, and the results of adaptive exploration applying to our research.
Okay, let's now talk about exploration and why it really matters in reinforcement learning. When an AI agent is learning, it's always faced with two choices, either to explore and try something new or stick to what it knows. This is the main difference between exploration and exploitation. Exploration can help discover new strategies, but again, too much work can cause learning to slow down. Exploitations, on the other hand, helps it stick with what works, but too much of that can lead the policy to do the same thing forever on loop. There should be a refined balance between exploration and exploitation. Now let's go through the problem statement. If we go through the traditional methods closely, we'll understand why they're not ideal. One, they rely on extreme external randomness. Two, they need manual tuning. Three, they cannot adapt as the training goes on. So the main goal of the paper is to get rid of all that manual work. In other words, make the network a little less noisy and let the agent figure it out for itself. That's the big idea behind noisy networks.
Now let's talk about the methodology. So the core idea is simple. We inject learnable noise directly into the network's weight and bias. So concretely, each parameter is written as mu plus sigma times a noise sample epsilon. So both mu and sigma are trained with gradient descent. So the agent doesn't just learn the policy, it learns the amount of randomness it needs to explore effectively. During training, we resample the noise when we update the network. Between updates, the network is fixed, so the agent's behavior is consistent across multiple timestamps, which creates structured state-dependent exploration that's very different from the action level indecisiveness like epsilon greedy. So this drop-in noise layer works with standard RL algorithms like DQN and dueling with replacement of epsilon greedy entirely and A3C. So these can drop the entropy bonus because parameter noise is already providing exploration. On the whole, instead of adding random actions or tuning exploration rates, NoisyNet it bakes exploration into the parameters themselves and it lets the agent learn how much noise to keep as training progresses. So that was the methodology, and now the core idea, that's NoisyNet. So looking at the core idea behind noisy networks, the main concept is to replace the fixed deterministic weights in a neural network with noisy weights. So you can see the formula here. So each parameter theta is defined as mu plus sigma times epsilon. Here mu represents the learnable mean of the weight and sigma is the learnable standard deviation that controls the amount of noise, and epsilon is the random noise drawn from the fixed distribution. So what's important is that this noise isn't static, it's learned through the gradient descent just like the rest of the network parameters. This means the agent effectively learns how much randomness to keep for optimal exploration instead of relying on the external randomness like epsilon greedy actions. That is, the exploration becomes an internal trainable part of the learning process. So this is the core idea behind the noisy network.
All right, so here's how it works. We apply noise to a typical linear layer. We replace the weights and biases with the parameters theta noted with the W and B subscripts, respectively. To obtain the noisy weight matrix and the bias vector, there are two options. The first option is the independent Gaussian noise, where each entry from both the weight matrix and the bias vector is drawn from the random Gaussian distribution. While it guarantees true randomness, it is very costly as you are computing PQ plus Q entries, where P is the number of inputs and Q is the number of outputs. The second option, factorized Gaussian noise, you use P plus Q variables from the same distribution and pass them into any real valued function. So for the weight matrix, each entry is the product of the function evaluation of input I and output J, while for the bias vector, each entry is just the function evaluation of output J. In the learning process, sample at each step of the optimization process using Monte Carlo approximation in the gradients. This will be the update to the noise parameters. Now to apply the noisy net to the reinforcement learning algorithms. When applying it to DQN and dueling DQN, instead of using epsilon greedy, the policy would optimize the action value function greedily. At each step, the connected layers of the value network are parameterized and the weights are changed. When choosing the action, generate another sample from the target function. This is the part where the model chooses the actions at the right place and at the right time. Similarly, the loss functions change when considering the noise. For the asynchronous advantage actor-critic model, they remove the entropy bonus of the policy loss. Again, the layers are parameterized just like before. Instead of epsilon greedy, it would choose the action simply based on the policy and it happens deterministically. To fix it, introduce an entropy bonus here for stochasticity. The result is that the gradients are unbiased due to the consistency of the network rollout.
The authors tested the arcade learning environment, a suite of 57 classic Atari games to test exploration efficiency across a range of reinforcement learning challenges. They compared noisy network across DQN, dueling DQN, and A3C, three strong deep reinforcement learning baselines. Each agent was trained between 200 to 320 million frames, averaging results across 3 random seeds for consistency. Performance was measured using the human normalized score. This means a score of 0 corresponds to a random policy and 100 matches human level performance. The results showed that noisy network versions consistently outperform baselines, with median human normalized score improvements of 48% for DQN, 30% for dueling DQN, and 18% for A3C. These gains demonstrate that learned parameter noise provides a powerful exploration mechanism that generalizes across architectures with minimal computational overhead. The researchers analyzed how noise parameters evolved over training. They found that some layers reduced noise, becoming more deterministic as the agent mastered a task, while other layers increased noise, sustaining exploration in uncertain contexts. This dynamic adjustment revealed that context-dependent exploration emerged naturally. The agent automatically balanced exploration and exploitation based on task difficulty and state familiarity. The mean absolute noise magnitude varied across games, showing that each environment led to a unique exploration strategy, a key strength of Noisy Net compared to fixed greedy schemes. In short, Noisy Net enables adaptive environment-specific exploration, learning when to take risks and when to stabilize, a hallmark of intelligent reinforcement learning.
NoisyNet delivers clear and powerful advantages over its baselines. It eliminates the need for manual tuning of exploration parameters, such as epsilon greedy or entropy bonuses, by learning exploration automatically for each environment. With proper noise scale initialization for stable performance, even individual network layers can adapt their parameters through learned noise, allowing the training of dynamic exploration adjustments. This approach is computationally lightweight and easily integrates into any reinforcement learning architecture. Despite occasional difficulties separating performance gains from improved optimization versus improved exploration, NoisyNet provides RL agents with adaptive curiosity that traditional exploration methods cannot achieve. This research directly connects to core reinforcement learning methods such as deep Q-learning, dueling networks, and A3C. NoisyNet shifts exploration from the action space, where agents randomly take actions, to the parameter space, where the agent's internal weights change slightly to create consistent, self-aware exploration, meaning that exploration becomes part of the learning process itself, rather than separate and manual tuning. This approach influenced later research in parameter noise policy gradients, Bayesian reinforcement learning, and distributional RL, where networks learn uncertainty directly from their parameters. Noisy net strengthens foundational, adaptive, and scalable reinforcement learning exploration, bridging traditional deep RL and modern uncertainty-aware learning frameworks. By replacing manually tuned exploration with learned parameter noise, NoisyNet enables agents to develop adaptive curiosity, improving performance and stability across deep RL algorithms. This unification of exploration and learning eliminates the need for human-intervened randomness, making reinforcement learnings more autonomous and scalable. Building on these principles, our next step is to apply NoisyNet with our Project 4 simulated self-sustaining microplastic extraction environment, comparing its performance against a baseline PPO model to evaluate whether adaptive exploration can further enhance learning efficiency. Thank you so much for listening, and we cannot wait to continue our shared findings and research with you all.